Right, so today is 4th April 2024 and today we are going to talk about GPT-3. Okay, so today we are going to talk about GPT-3. Now the title of GPT-3 is T5. I decided not to do that. Okay, I mean same transformer encoder decoder style, okay, that same thing. So what you will need to know about is what is the D model. Okay, so let me look at the table. You know, that same old story. So the biggest takeaway of T5 is what? This unification of tasks, right, where they are, you know, there are so many different tasks in NLP like summarization, question answering, translation. They are able to make a unified task from all these tasks. This is the main takeaway. Baki, you know, so let me see. Yeah, so they have this table. Yeah, not this one. I'll have to search for the table, maybe I'll do that later. Yeah, so here they have it. So for example, 3 billion and 11 billion, what they have is, so D model is 1024, 24 layer encoder and decoder, and the, you know, in the feed forward neural network. So they go, so what was this value for others? It was like 3072, 2048, you know, we were talking about this feed forward neural network. So you had D model cross something, DFF. So this DFF, they keep it huge for 3 billion and 11 billion, they keep it 16,384. So D model, which is 1024, and then 16384, and then back to 1024 again. So this is how they increase the number of parameters. But I don't see anything, you know, that you can't really understand there. So I'll leave T5 at whatever we had done in the last class. Now, so title of GPT-3 is language models are what was the title for GPT-2? Language models are, so until here they stay the same. GPT-2 was, so this is GPT-3, but 2 was unsupervised multitask, and then come here again, right. So this word few, I mean unsupervised multitask is replaced by few shot, and this paper is essentially just the continuation of GPT-2 paper, where they ended with this figure, you know, where with model size you had decrease in perplexity, but it had not saturated out. Remember that curve? So it was something like this. So this was 117 million, and then this was 1542 million, and then they said that this, so this had not actually, so on this side you have perplexity, which is basically a performance measure for language modeling. So with increase in parameter size, this thing has still not kind of plateaued. and if this has not plateaued, what can we say? There is a room for increasing the number of parameters so that I can get a flattened curve there, right. So, this is where we start. Now, so language models are few short, this is GPT-2. So, language models are few short learners. Okay. So, again they emphasize this so many times. First is, so the trend has been of what? Pre-train and then do what? Fine tuning. So, they say that this has been largely the trend of almost all models in last few years. So, we have seen this for all the papers that we have talked about. Now, and so what are the problems with this method? So, what are the problems with fine tuning? See, pre-training is a nice thing. You do it on some task, you do it for the full data set. So, this kind of gives you some kind of language understanding. Language understanding. What about this? What does this achieve? So, once your weights are good to tackle this task, which is usually language modeling in case of decoder only, and which was masked language modeling for BERT, and which was, what was that for T5? What did they call that? Denoising thing. Okay. So, where they are given a particular sentence with particular words or tokens masked, and then the model is supposed to output the correct sentence. Or in fact, model is supposed to output the values of masked tokens. So, fine tuning, you require something like 100k examples. So, they have been arguing this starting in the GPT-2 paper itself, that fine tuning actually ruins things. This whole combination is good, but you pre-train something, this model becomes really good at understanding the language, but then you start fine tuning that model for each particular task. You do it for summarization, you do it for, so basically for every NLP downstream task, you fine tune this same base model in a different manner. So for every task, you are going to take this one as starting point and train it, fine tune it again. Okay? For every task, you are supposed to fine tune. This is something they say is not a good generalization, right? Because for every task, earlier you were doing, your architectures were task based. Now here we are saying architectures are not as such task based, architectures more or less remain the same, but your fine tuning is task based. So still things are attached to task based in some sense. Now, and one of the biggest takeaways of GPT-3 is scale. Scale means increase model size, and that helps automatically to improve performance on all these things. So scale in itself is a big deal. This is what we saw in GPT-2 paper at the end of it, and now, so they basically want to continue from here. So specifically we train GPT-3 on an auto-regressive language model, which basically means decoder only, with 175 billion parameters, 10x more than any previous non-sparse language model. Okay? And here we show that scaling up language models greatly improves task agnostic, few shot performance, sometimes even reaching competitiveness with prior state of the art fine tuning approaches. What does this mean? Let me repeat. Here we show that scaling up language models greatly improves task agnostic few shot performance. So what does task agnostic mean? We show that scaling up language models means bigger size, improves task agnostic, few shot performance. So if you increase the model size, right, so that improves your task agnostic performance. Task agnostic means the model cares lesser about whether it's a summarization task, whether it's a translation task. So bigger model is more capable of absorbing this fact that if you give me diverse tasks, I will still be able to perform better. So a model of size 1.5 billion will perform much worse compared to a model of size 175 billion. On what? When you have diverse downstream tasks. If your model size is small, which is the way to go? Yeah, so that's the right question to ask. If your model size is small, which is the way to go? So pre-train and then fine tune, because your model does not have the capacity to become task agnostic. Task agnostic means where you are not supposed to tell as such, at least not in terms of fine tuning, you are still supposed to tell in some sense, but you are not supposed to tell in terms of fine tuning where you train hundreds of thousands of examples, the pre-trained model, right, and you run everything again. Questions here? I see so many faces that are not in sync. Questions? Task agnostic simply means if you want to, so you are pre-trained on one task, let's say language model. Now you want to use that same network for summarization, translation, NER, NLI and so on. So all these tasks, right. So if you want to use this kind of schema for translation, you pre-train on which task? Pre-train on so if you are talking about just decoder only transformers, you pre-train on which task? I am talking about task, language modeling. अब क्यों बोल रहे हो? तो रिपीट ही तो करना था. So you pre-train in case of decoder only on language modeling. In case of BERT, this was masked language modeling, right? So once you pre-train is again only training only. Pre-training is training only, right? You are finished training on one task. In case of decoder only, that one task is language modeling. In case of BERT, that task is masked language modeling. Once you are done with that thing, you do fine tuning. You add one more layer, right? And then you fine tune. Fine tuning means potentially you can change all weights of the full model, right? So all 1.5 billions potentially. Of course, you can freeze some, but if you want, you can train all. So this was one way of doing it. You pre-train on a task and then you do fine tuning task specific, right? So your fine tuning will be for summarization, you can do it for translation, you can do it for NLI and so on. This is task specific. What will be task agnostic on the other hand? that you do training in a sense that you don't have to fine tune on each of these for a particular task. So then that model becomes task agnostic. And here in the abstract itself, what do they say? They say that scaling up actually gives you much better performance on task agnostic. So if your model is small, right, the way it is done today, you can't expect your model to be doing well without telling me the task, or in other ways without doing fine tuning. But if your model is big, then you can expect the model to do good on, so you train just on one task and expect it to learn doing other tasks as well. Yes. See, the argument here that is usually given is something of this sort. So human beings, for example, we have been learning languages throughout our schooling and everywhere through interactions with each other. Now let's say if somebody comes and asks you summarize something, right? So think of a human being who has never heard of this task, individual task called summarization. But given that if that person has a good knowledge of language, can you think that person can still summarize? Because if you understand meaning of summarization, you are given a large chunk, you can simply write a small summary of it. Or if you know both English and Hindi, I don't need to show you thousands of examples of English and Hindi parallel corpus to be able to enable you to learn translation. I give it you first example and you know what is the task, what am I supposed to do. The same analogy is given here as well, that once a model has learnt good weights through training on, let's say, language modeling, then it enables it to do all these downstream tasks in a much more efficient manner. Okay. So for, and then they test its performance in few shot setting. So they test the performance in the few shot setting, we will come to it. For all tasks, GPT-3 is applied without, so write this down, for all tasks, for all these tasks, GPT-3 is applied without any gradient updates or fine tuning. So GPT-3 does not do any fine tuning. With tasks, right? So with task you don't do fine tuning, with task you don't apply any gradient changes, gradient updates. With task and few short demonstrations specified purely via text interaction with the model, right? And GPT-3 achieves strong performance on many NLP dataset like translation, question answering, closed task. Closed task is same as your masked language model. Okay. And then they also report some task where GPT-3 actually struggles. So it's a long paper, 75 page long. Of course, we are not going to do everything. We are just going to take the main takeaway. And main takeaway of this paper is, we already know. What is it? Scale. Okay. Yes. Yes. Okay. So, right. So let us continue. So, you know, they do something like this. I mean, this is a figure in the paper, but so in this direction you are doing, that's what we expect that this is going on, yes. So, that is why if you follow news in this area, OpenAI has already been saying that with 1.75, 1.7 trillion parameters in GPT-4, the performance due to scaling has almost stopped. So, at the end of this paper, they will still say that there is still room to scale up. So, from GPT-3 they go to GPT-4 with potentially, so there is no official information on this, but people expect that the number of parameters there are 1.75 trillion. Okay? So, that is again 10x of GPT-3. And then after that you see these news from OpenAI that now scaling does not really help. Okay? So, learning via SGD during unsupervised pre-training, and what they say is something called in context learning. Okay. So, in context learning means somewhere during your data set you must have seen things like and so on. So, where you are correcting actually spellings, things like so I am writing it in the paper, they are writing it French, but let us write Hindi. Okay, and so on. So, what they claim is during this training your corpus is huge. So, in the corpus itself, during this training your system has seen things like, so and this is the example they provide in GPT-2 itself. So, in GPT-2 paper and here as well they say, so what is the corpus that GPT-3 is trained on? The corpus is huge. So, for GPT-2 which corpus they collected? Web text, which was from Reddit links. But then what did T5 bring onto the table? Common crawl, okay, and common crawl was of size 20 terabytes at that time, and they reduced it to 750 GB, did not use all of it for training, they used a much smaller chunk of that. So, they do further filtering of common crawl, the same that was used by T5, and they reduce it to 570 billion tokens rather than 570 GB rather than 750. Okay. So, they filter it much more, and what they use is common, so number of tokens, common crawl 410 billion. So, these tables are given in the paper, and this table was quoted as it is in the NYT lawsuit, because they say that web text forms 22% of GPT-3 and onwards models. So, they rely too much on web text 2, which they call high quality data, but they do not pay NYT in any manner, no loyalty, nothing. Okay. So, it was trained on books 1 corpus, books 2 corpus, English Wikipedia, web text 2, common crawl, filtered. Okay. So, it is a huge data set, and so total somewhere around 500 plus billion tokens. So, everybody is okay with what we are trying to say here. So, for example, in your huge text corpus that you are training for language modeling, you might have seen things like, so this whole thing, so things like this whole thing can be summarized as. So, they claim that the model should be able to learn that whatever follows is a summary of whatever was there previously. So, in your big corpus of 500 billion tokens, they say you have seen all kind of tasks. You have seen people saying thanks means dhanyavad in Hindi, or thanks means merci in French, and so on. Okay. I just talked about this thing. So, this is what I just talked about. So, they also say that model starts learning doing arithmetic too, but these kind of things where they are automatically able to correct the words. So, if fish is spelled as FSIH, the model is able to correct it. Or if you have seen things like thanks is merci in French, and so on. Okay. So, this already tells you so if you see, if you want to do few shot learning, which is this range, number of parameters are small, there is no few shot learning happening there, right. But if your number of parameters is large, then you have few shot accuracy increased up. So, if number of parameters are small, few shot accuracy is actually very low, but if you scale the model up, then few shot performance actually increases. And this doesn't seem to be plateaued out yet. So, what they want to do is increase this further. Okay. So, in this figure all they want to say, I mean not to be taken literally, but they say, so what can be few shot? Guys, what is few shot? So, some examples of the order of 50 to 100, not 10,000 or 100,000. So, few shot is different from fine tuning. We'll compare them. So, let us first go to that comparison. Right. This one. So, fine tuning means the model is trained via repeated gradient updates. So, this is the difference between fine tuning and what was that? Few shot. In few shot, you don't do any gradient updates. This is an important thing that you should know. Fine tuning, the model is trained via repeated gradient updates using a large corpus of example tasks. So, if you are doing, for example, so this table is given only for translation. The model is trained via repeated gradient updates. So, when you translate whatever to whatever French thing, you actually update the gradients. That is your fine tuning. But in case of few shot or one shot or zero shot, in addition to the task description, remember what was the outcome from T5 paper? Instead of computing probability of output given input, you should be able to compute the probability of output given input and task. So, here you are giving that task, translate English to French and then give it example. So, a few examples you give, and the last one you are expected to, so model is expected to figure out what should come here, and this is done during test time, not training time. This is what you done during evaluation time. No gradients are updated. So, you are not training it for this. What you are saying, it has trained enough. I show it a few examples. Will it be able to come up with a correct completion in the last? Okay. And what will be one shot? Just one example, and then next time you ask a question, what should come here? What will be 0 shot? So, no example, directly you ask a question and you expect that the model should be able to figure out what should come here. Okay? And we see performance of GPT-3, GPT-4, I mean these days whatever the systems that we interact with, right? They are much better than those fine tuned systems. So, we are still talking about a 2020 paper. Okay. So, the important distinction between fine tuning and these few shot, 1 shot, 0 shot is what? In fine tuning you upgrade you run gradient descent and you update the parameters. In all these things you are not doing it, you are asking these questions at the test time and the model is expected to figure out that whatever. Okay. Now, so we go back to the figure that I was showing initially. This one. So, what they simply say here is aggregate performance for all 42 accuracy dominated benchmarks. So, they evaluate GPT-3 on these 42 accuracy dominated benchmarks. So, only those things where accuracy is the parameter. What do you understand from this figure? Huh? So, that right, accuracy increases with model size and this prompts them to go even further, this 175 billion, right, because if you see it is nowhere close to plateauing out, it is rather still linearly increasing. Okay. So, if your accuracy is somewhere close to in the range of 40 and now it is higher for few shot as expected because you are giving me examples, and then lesser for 1 shot and then even lesser for 0 shot. What are these other curves in the background? This figure says no. When you give multiple examples, you perform better. What are the curves that we are seeing here? See, so we do not really care, but these are 42 curves on these tasks, whatever these tasks were. And when they run GPT-3 and take an average, so from this particular graph, you can only take away 2 broad things that actually make sense. One is with increase in model size, your accuracy of 0 shot, 1 shot and few shot is increasing. So, you still have room to improve the model size here first. Second, there are so many tasks for which GPT-3 is already doing better. So, if you see GPT-3 is doing better compared to these tasks and still has room for improvement for those kind of tasks, right. So, GPT-3 in itself is still able to do better than some of the tasks, but still struggles to do well for other tasks, right. So, this is a very crude comparison, only as I said only 2 takeaways. One is if I increase model size, I have rooms for improvement, and second, some tasks I am already doing better and some tasks I am really struggling to do on. So, if you see here, the approach, our basic pre-training approach including model data and training is similar to the process described in this is GPT-2. Okay. So, there is not much to learn there, except one thing they say somewhere in the model that we will see. So, we know what is fine tuning now. Fine tuning we know already. And if you see here, few shot is the term we will use in this work to refer to the setting where model is given a few demonstration of the task at the inference time, not at the training time, as conditioning, but no weight updates are allowed. So this you do during the test time, not the training time. Okay. And then few shot, then one shot is same as few shot, except in that case example is just 1 and so on, 1 shot and then 0 shot. So this is, and now you can understand the madness here. So GPT-3 small, 125 million, which is close to GPT-1, number of layers 12, D model 768, number of heads 12, D head is 64. So this is actually GPT-1 only, right? I mean, this increases because they have increased the vocabulary size from 40,000 to 50,500 roughly. So GPT-3 has 50,500. How much GPT-2 had? So either GPT-3 has vocabulary size of 100K or 50K, one of these two. Okay. Now GPT-3 medium, now this is closer to BERT large, number of layers 24, D model is 1024, number of heads is 16, D head is 64, and I will talk about those things later. GPT-3 large 760M, 24, D model is now 15. What was D model? Right. So your input will be 1536 dimensional now, and everything that gets output from all these layers, everything will now have dimensions of 1536, number of heads is 16, D head is 96, it is not 64 anymore. Okay. So they have changed, and just directly go to the last one, 175 parameters, number of layers is staggering 96, D model is 12,288, number of heads is 96, and each D head is 128 rather than 64, and batch size is huge compared to others as well, and learning rate. Okay. So as your model size increases, you kind of decrease the learning rate. So GPT-3 is what? A super big GPT-2. Okay. GPT-2 was somewhere like this. GPT-2 was somewhere like this, right? But it was, I think, 64 only. But GPT-3 is huge, 96 decoder only layers. So this is what gives the number of parameters here. Okay. Let me see if I have somewhere detail. Right. So here they say we use the same model and architecture as GPT-2, including the modified initialization, pre-normalization and reversible tokenization described therein, with the exception that we use alternating dense and locally bounded sparse attention patterns in the layers of transformers similar to the sparse transformer. What they might be doing here in this sparse transformer thing? See, what are the negative sides of transformers? Why should we not use transformers? What is wrong with transformers? In particular, so if you see here, the context size for GPT is 2048 tokens. So capital T is in this case 2048, D model is 12,288. So, this is a huge model. Now, what will be wrong or what will be computationally heavy? What do you do? How do you compute self attention? So, in self attention layer you will have order n square, order n square computations, right? How? Your context size is, so if your context size is 2048, your output will be 2048, and for every output you will be computing dot products with 2048. So, these are potentially 4 million dot products of size 12,288, right, and then you have to compute softmax and all this. This is computationally heavy. So, what they say is, instead of doing the normal self attention, we do as it is done in this sparse transformers. So, there you don't do order n square attentions, you rather do order n under root n. So, that gives you some speed up. Other than that, that's it. So, training data set. So, you see here, this is an important thing. This size of data set, the common crawl constituting nearly 1 trillion words, this size of data set is sufficient to train our largest models without ever updating on the same sequence twice. So, how many epochs basically? How many epochs basically? This size of data set is sufficient to train our largest models without ever updating on the same sequence twice. How many epochs? 1, right. So, you do not do things like epoch 10, epoch 100. The data set is huge, you do not need to see the same sentence again in principle, but in the details they tell that that in the details, if you go to appendix, they tell you that there is a higher weightage given to these data sets compared to this one. So, you can see here, even though the quantity of tokens here is 410 billion. So, if you will compute the percentage, it will be much more than just 60%. And if you compute the percentage of web text too, it will be much lower than 22%, but this is still given the weightage of 22% because of the high quality that they cite, which is precisely the reason NYT sues them, that you have scraped all our data, right, call that high quality, do not pay us and make money yourselves, and then do not pay us anything. Okay. This is fine. Training process. Okay. So, somewhere, yeah, so before training process, so if you see here, they want to, so they can have some contamination. What is that? See, a major, so a major methodological concern with language models pre-trained on broad swath of internet data, particularly large models with the capacity to memorize vast amounts of content, is potential contamination of downstream tasks by having their test or development sets inadvertently seen during pre-training. What does this mean? So pay attention only here. See, you have basically crawled the whole internet, right? So most likely the data set on which you are going to evaluate your models on, most likely you have incorporated them in your training data set as well. So if you evaluate on the same data set on which you have trained a model on, that is not the right way to do. Remember, what do we do? How do we do machine learning? We let us say take 80% for training and we keep another 20% for test time, because we want to run it on, we want to test it on unseen data. But here argument is, if you have downloaded the whole internet and then training on that, most likely whatever things you are going to test this on, it has already gone in training data set. So they say, to reduce such contamination, we searched for and attempted to remove any overlaps with the development and test set of all benchmarks studied in this paper. So they try to kind of segregate training and they try to take out those things which they are going to test. So they try to remove that from training data. But the funnier part comes now. They say, unfortunately, a bug in the filtering caused us to ignore some overlaps, and due to the cost of training, it was not feasible to retrain the model. So in section 4, we characterize the impact of remaining overlaps, and in the future work, we will more aggressively remove data contamination. So they say that cost of training is so huge that after realizing that there was a mistake, we couldn't retrain this, and the results in the paper are still, with that contamination. Now, I don't see anything that is important and is left. That is it, more or less. Except maybe, just have a look at this graph and we go. So y-axis is which scale? Which scale? Log scale. Okay. So this, if this is somewhere around 2, 3, GPT-3 with 175 is somewhere around, no? So close to 4,000, something like that? No, 4,000. It won't go 5 because it is halfway, but somewhere around 4. Okay. So if it took you, whatever, 2 units of compute to train BERT base, it took you 4,000 units to train GPT-3. And if I remember it right, I somewhere heard, this was equivalent to, No, that was for GPT-3, which is even worse. Okay. I had heard something like, a year of training on 1 GPU or something like that. All right, so that is it for today.